Welcome. Oh, don't need to write the word welcome. To page 35. This is on the extended GCD. So, the great GCD, the Euclidean algorithm computes it's actually the extended Euclidean algorithm, named after Euclid. It's one of the oldest algorithms that's ever been described as an algorithm in human history. But we're studying it because it's the tool that will allow us to compute the magic D for decryption in the RSA. So it turns out we can take the given public information, N and E, and if you can factor in into P times Q, then we'll see later that we can compute from P and Q and E, we can compute the magic number D rather. Okay, so we say a number divides, or is a divisor of another integer if there's some way to write it. So we say D divides A is just a shorthand for means A is equal to D times something. Okay, and the greatest common divisor is the largest integer that divides both A and B. So in elementary school, you probably learned this for working with fractions. So if you had something like 32 over 60, you cunningly figured out that the greatest common divisor, there's a bunch of 2's there, so you figured out the bottom is 4 times 15 maybe, and the top is 4 times 8, so you could cancel the 2's. So that algorithm where we factor the numbers into prime factors and then cross off the ones is ridiculously inefficient. And if we had to use that for our purposes, we'd be doomed. But the GCD comes up with it in a much more efficient way. So when you do grade school division and you divide a number A by a number B, the number you write up here we're calling Q, and you multiply back down and subtract. And the number down here we call R. So the equivalent way to write that in mathematical form is that A is equal to QB plus R. A is equal to QB plus R. So we're finding the most number of B's you can subtract from A is Q, and then you're left over with R. And of course this is with 0 less equal R less than B. So the remainder is always smaller than the thing you're dividing by. Okay, so now we're going to prove a really important fact, that given this division problem, the greatest common divisor of A and B is equal to the greatest common divisor of B and R. That may be surprising and look but that's turns out to be true. So let's prove it. So if D divides, this is the notation we use for that. If D divides A, let's see, I want to look here at the notes, and D divides B, what does that mean? Then that means that, we could write this all out. Well, so we want to prove that if D divides A and B, then D divides B and R. So it's obvious that D divides B because D divides B, right? We assumed it. Okay, and the exciting part is to prove that this divisor of both A and B has to divide R. And to prove that, we just write R is equal to A minus QB from this fact up here. So since R, it turns out it's pretty obvious that if a number is divisible by if D divides A and D divides B, then obviously it divides anything like this where you add or subtract them and multiply them by stuff. Okay, we won't bother to bring in the box here in the description of division. Okay, for the other direction, so that's kind of the easy way. So if D divides B and D divides R, we want to show then D divides B. So now we're trying to do the converse, that if D divides B and D divides R, then D divides A and D divides B. So if D divides B, D divides B, but now we want to prove that D divides A, but A is equal to QB plus R. Oh, so this is the easy direction. So if D is a factor of B and a factor of R, then it's also a factor of that combination of them, which will be a factor of A. So that was pretty quick and dirty. If this were discrete math, we might have done it a lot more carefully. So the cool thing from a computer science point of view is if you look at the top of page 36, there's some code there. And that code is the recursive version. It says to do the GCD. So let's go to another page. So it says the code is based on the GCD of A and B is equal to the code basically is do the division to get Q and R, and then return the GCD of B and R. That's if A and B are not equal to 0, and otherwise you return A or B. The trivia, when you get to the bottom, it's pretty obvious. Okay, so let's just do an example of that. So the example, let's say we want the GCD of 1861 and 757. So we start with, we'll make ourselves a little chart. We got A and B, and Q and R, just keeping them in the order of the theory. So we start with 1861 and 757. So the recursion says divide 1861 by 757 to get the quotient and the remainder, and then we can go from there. So I've got to divide 1861, and this is just like we've been doing. So 1861 divided by 757. So 1861 divided by 757 is, the quotient is 2, as the answer is the calculator gives 2.458, blah, blah, blah. So, and just like we did with before, to get the remainder, we subtract the 2 and then multiply back by what we're dividing by, which is 757. And that's how we get the 347 for the remainder. If you don't believe it, you can check out that 2 times 757 plus 347 is equal to 1861, presumably. Okay, and then now here's the exciting thing. The exciting thing is this recursive fact here on the previous page says now the GCD of these two numbers is equal to the GCD of B and so GCD of A and R is equal to GCD of B and R. Sorry, the GCD of A and B is equal to GCD of B and R. So here's A and B, here's B and R, so we just promote. So the columns maybe should be switched, but that's life. So now we just continue that. So I'm going to bomb through this. 757 divided by 347 is 2 point something. So it's a quotient of 2. And I subtract the 2, get 0.18 something times the bottom, which is 347, and I get 63. Okay, then I promote, guys. 347, 63. Do 347 divided by 63 is 5 point something. So I have to write down the 5. And then multiply back by 63, so I get 32. And of course all these numbers are in the chart in the notes. Okay, then I promote. The recursion says it's GCD of B and R. So how many times does 63 go in, 32 go into 60? Only once. 64 would go in twice with a remainder 0, but 63 it goes in with a remainder of 31. So now I can do them by hand. So then I promote 32, 31. So be careful. So the goes in once with a remainder of 1. You have to be very patient at the end and not get carried away. And then 31 divided by 1, the quotient is 31, and the remainder is 0. But we keep going. So we promote the B to the A and the 0, and now then we stop. So that's the base case. When one of them hits when either A or B hits 0, The other one is the GCD. Okay, so, and we'll always want to get 1 at the end. If we don't, there's something wrong with our RSA setup. So so that's very exciting. So let's go on to the next page, and we'll look at what we really want. So that's just the warm up. Okay, so here we are on the next little chunk section of this. The extended GCD is extended Euclidean is a very powerful idea. And so we want to look more closely at the following fact. And in fact, we're not only going to prove it, we're going to get the algorithm for finding it. So it turns out the greatest common divisor of A and B, whatever that might be, we want it to be 1 typically, is equal to SA plus TB for some S and T. So you can always find integers that are, if you kind of do you multiply A and B by those integers, that you can get the combination to give you the GCD of A and B. Okay, so we're going to prove that by induction. So we're going to induct on the number of calls. So the base case, so basically when you do induction, you're working with recursion. The base case is, say, B equals 0, okay, and A is not 0. By the way, we'll always put the bigger of the two numbers we're doing the GCD of on the leftmost column and call it A. So we'll always end up with B equals 0 when we get to the bottom. Okay, so in that case, in the base case, can you find, so what's the GCD? In that case, the GCD of A and B is just A, and can you find numbers that will do something times A plus something times B equals A? Sure, we just put in 1 and 0, although that doesn't even matter. W, I was just looking at the notes. Okay, so that base case is easy. So we're going to assume the result is true for, the fact is true for B and R. I guess that's the way we can say. So we're going to assume the GCD of B and R can be expressed in this way, but for the notation we're using, we're going to call this S prime plus T prime times R. So we're saying that we can get multiple integer multiples. I should have said that. These guys obviously have to be integers. So the GCD of B and R, we're assuming that inductively, and now we want to get numbers for the GCD of A and B. So this just turns out to be some simple algebra, because what do we know? Well, we know that this is equal to the GCD of B and R. So we know that the GCD of A and B is equal to S prime B plus T prime R. But we'd like that to be a combination of A and B, right? So we want to get rid of the R. So how can we get rid of the R? So what do we know about R? Well, as always, R is equal to, well, we have A equals QB plus R. So R is equal to A minus QB. So if we plug that in, we have the GCD of A and B equals this, which equals this, which equals S prime B plus T prime, and R is A minus QB. And if we clean that up a little, so that's S prime B plus T prime A minus T prime QB, which gives us something times B plus something times A. So it's T prime times A. I've switched the order here accidentally. and then the things that are multiplying b are s prime and minus t prime q. So that's pretty amazing. So just to clean it up, so it's t prime times a plus s prime minus t prime q. This would be a good place to say that these primes do not represent derivatives. Okay, so that's exciting, and why, we'll see how exciting it is. So what does this say? This says that if you have the GCD of B and R expressed, then you can express A and the GCD of A and B. So that lets us, so that finishes our inductive fact. So we call this guy S and this guy T in our original proof. So that concludes that. So now let's look at the code, but just a smidge, but then we'll look at the example. And that will conclude our work with the extended GCD, which is a very powerful thing. So next page. Okay, so there's code in the same place, probably, code / RSA. I kind of gave it that generic name, but it's also on the top of page 37. So if you look at the code, it's just saying, when we do the call to GCD, we not only want it to return, we want it to return an array of integers, we want it to return the GCD in spot 0, and we want it to return the S and the T in spots 1 and 2. So if you look at that code, take a minute to look at the code, maybe even pause the video, you can make sense that it's really the same as the formulas. So x of 0 is what we've been calling the GCD of A and B, which is also the GCD of B and R. And I think x of 1 is actually S, and x of 2 is T in the terms we've been using. But more importantly, let's do the example. So this is going to be exciting. All right, so we start off with A, B, Q, and R, and now we're going to tack on S and T. So I'm doing a different, oh no, I guess I'm doing the same example. Ha, excellent. So that means we can just copy down all the previous stuff. So I'll do that, 1861, 757, 340. You know, I'm going to make a point of what's going on, I need to make lines. This extremely sophisticated software, I'm sure I could do that. I'm just doing it the easy way. 347, 63, 32, 31, 1. And the B is 757, 347, 63, 32, 31, 1. And then the Q's are 2, 2, 5, 1, 131. And we don't bother with the Q there because that was the base case. And the R is 347, 63, 32, 31, 1, and 0. And the S, all right, now we want to get the S's. So at the very bottom, so the point is, this is the GCD of everybody in this chart. So the GCD recursively of every pair of numbers is 1. So the GCD of 1 and 0 is 1. So can we express 1 as, we want 1 equals something times 1 plus something times 0. That was the base case in our proof. So of course we can take 1 here and 0 here. And we could actually take any numbers t, anything, right? Because this, whatever we use there, any number, it would go away. But 0 will keep all the numbers as we work our way back up as small as, probably as small as they can be. Okay, and we'll come back to look at this first choice later. Okay, so the formula simply says that, so these guys are the primes. So this is S prime and T prime. So when we back up, the formula we've just proved says S equals T prime. So that just means we put a 0 there. And then the other one says T on this row is equal to S minus Q T prime. So t prime is 0. So it just becomes a 1. So that's kind of boring there. Okay. And now these are s prime and t prime, and we want to get s and t for this row. So, oh, and we should always check it. The check, I'll just say that, check. So the check is 31 times 0 plus 1 times 1 equal to 1. Yes. Okay. You're foolish if you keep working back and doing the arithmetic without checking at every step to keep from screwing up. Oh, and on this step, 1 times 1 plus 0 times 0 equals 1. Okay, so now I advance the s becomes the lower t, and now this t here is 0 minus q times 1, so it turns out to be minus 1. And if you check, you'll never make a mistake with signs or anything. So does it work? Is 32 times 1 plus 31 times minus 1 equal to 1? Yes. It's 32 minus 31 is 1. Okay, then we do another notch up, minus 1, and then this will be 1 minus 1 times 31, which turns out to be, what, 32? No, wait a minute. Oh, I'm doing something horribly wrong. Oh, sorry. Yeah, it's really important to use Q, not R. So the Q is actually 1, and it's the Q from the row you're on. So 1 minus 1 times 1 turns out to be 2. So the check here is really important because I screwed it up. So is minus 1 times 63 plus, I'm going to move this over for a sec, minus 1 plus 63 plus 2 times 60 times 32. Is it equal to 1? Yes, it is, because it's 63 minus 63 plus 64. Okay, so that's important. Okay, then so that the two there comes up, and now we can get on a roll. So we're taking this minus 1 comes over, gets multiplied by the 2 below, so that's minus 2 times, sorry, it's this number, right, s, so s, it's minus 1 minus q, but q here is 5, and t is 2, so it's minus 2 minus 10, I think is minus 12. Wait a minute. No, sorry, it's minus 1 is the s coming up, and we're subtracting that from q on this row is 5, and t from below is 2. So it's minus 1 minus 5 times 10 is minus 11. This is so messy. So I'm all hunched over. Okay. So, and of course I cheated a little. I looked at the answers on page 30, whatever. 38. Okay, so now it goes minus, oh, and check it. So is 2 times 347 minus 11 times 63? What is that? So 2 times 347 is 2 times 347 is 694. And 11 times 63 is 693. I didn't just make those up, it's really true, so it checks, yay. Okay, so here we get minus 11, so then we take 2 minus q, which is 2 times minus 11. So that ends up being 24, right? Okay, and I should check that, but since I've done it by the computer, I won't bore you with that. So we boost it one more level, 24, and then this should be minus 11, minus 24, or minus 24 times 2. So that's minus 11 plus minus 48 is minus 59. So the 24 and the minus 59, that's the whole point here. The final check, which is the only one you really need, is that if you take 24 times 1861 plus minus 59 times 757, our two original numbers, what do you get? Well, 24 times, son of a bitch, times 1861 is 44664. And then that'll be minus 59 times 757, which is 44663. Which comes out to 1. So it checks. Yay. Okay, so that's great. Let's go on to the next page. So the you should now do embedded exercise 27. So what is this? It's simply asking you to do the extended Euclidean extended Euc algorithm for doing the GCD of 439 and 211. And in particular, we want the S and the T. They're the important guys. Okay. And so pause the video, and when we come back, we'll work that out. Okay, welcome back. I hope you actually did this. So there's a point to doing this besides the just another example, I believe. So let's check it out. But we'll kind of do it. Ooh, and I don't have the answers to this one, so you could have to see if I screw up. But if I'm checking, I can't screw up too badly. All right, so I have A, B, Q, R, S, and T. Okay, so we start with 439, 211. So the first division, so we take 439 divided by 211 is 2. So I subtract the 2, I get 0.08 something times 211 is 17. And of course, remember, you don't do the S and T till you're on your way back up. Okay, and now I recurse. The GCD of that is the GCD of this. So 211 divided by 17 is 12 something. So subtract the 12 to get 0.411, multiply that back by 17. I get 7, and I promote to 17. And now I'm happy because I'm getting where I can do them by hand. So I have GCD of 17 and 7. And so how many times? So 7 goes into 17 2 times. That's 14 with the remainder of 3. Promote to get 7 and 3. So 3 goes into 7 twice with the remainder of 1. Promote. 3 and 1. 3. So 1 goes into 3 3 times with the remainder of 0. Promote and stop. Okay, so at this point, I'll demonstrate my skill at drawing horizontal lines for a minute. Okay, at this point, we traditionally do is, what we did before is we used 1 and 0. And the check is 1 times 1 plus 0 times 0 works. Okay, yay. Now, then our algorithm said this becomes 0 and this becomes 1 minus Q times that. So that's just 1. And the check is it's 3 times 0 plus 1 times 1 is 1. Yay. So I do 1, and this becomes 0 minus 1 times 1. 1 times 2. So this becomes minus 2. And the check is 7 times 1 is 7, plus 3 times minus 2 is 6, so that works. Check. Oh, I'm not going to check those because I want to use this space in a minute for the point of this. Okay, so now keep going. Minus 2. This isn't going to be so bad. So it's 1 minus 2 times 2. So that's 5, I believe. So that's minus 34 plus 35 is still 1. Yay. Okay, then next to last step, 5. Then we get minus 2. 12. Q is 12 times 5 is 60. So minus 2 minus 60 is minus 62. Ooh, do we believe that? Let's check it out. So 211 times 5. So we want to check that 211 times 5 plus 17 times minus 62. So minus 17 times 62 equals what? So 211 times 5 is 1055. And 17 times 62 is 1054. Okay, good. I haven't screwed up too much. See, you can see how this number theory stuff works out. These results are kind of unpredictable. So finally we get minus 62, and we get 5 minus 62 times 2. Yuck. So that's 62 times 2 is 124 plus 5 is 129. So does that check? So is 439, this guy, times minus 62 plus 211 times 1, yeah, I'm doing them backwards, but you get the idea, hopefully. So let's do that. 439 times 62 is, so this is minus 27218, and this is 211 times 129 is my 27219, which is 1. Yay. Okay, so it worked. So why did we do that? What's the point of this? Well, the point is we could have done different S and T, and sometimes you have to. So it turns out later we're going to want to always have a positive number here, okay? So if you track what happened here, this 1 went up to here, so this was positive, and these alternate, positive, negative, positive, negative, positive. So we actually, if we want this one here to be positive, we need to start at the bottom differently. So an easy way to do that is to do 1 and 1. And you could check it out now. So this is going to go here when we move it over, and this is going to be 1 minus, so this is just going to be what? Oh, this hurts my brain. Okay, first of all, does 1, 1 work? Yes, because it's 1 times 1 plus 0 times 1, so it gives us 1. So when we move this over, and then this becomes 1 minus, there's something horribly wrong. Oh, I'm not looking at, I keep looking at, yeah, be careful. I keep missing the Q column and looking in the R column. So this is 1, the guy from the row below, minus the guy below, which is 1, or minus the Q times the guy below. So with a 1 there, this becomes minus 2, 1 minus 3. And does that work? Sure. 3 times 1 is 3, plus 1 times minus 2 is 1. So you can see now this is going to go positive, negative, positive, negative, positive, which is what we want. So let's just finish it off. So then this becomes minus 2, and then this becomes 1 minus 2 times 2. So what is that, 5? Yeah. I said yeah, because 7 times minus 2 is minus 14 plus 15. I hope I'm not being too redundant. Okay, minus 2 times 5, so it'll be 2 times 5 is 10. That'll be added to the minus 2, so it's minus 12. So we live bravely. So that's 85 and negative 84. Ooh, I could check that in my head. So then this will be minus 12 times 12 is a minus 144 subtracted. So it's 144 plus 5, I think, is 149. That looks weird. So let's check it. 211 times minus 12 versus 17 times 149. So 211 times 12. I'm getting kind of tired. So that's minus 2532, and 17 times 149, 2533. I mean, that's what it's supposed to do, but it's just heartening that it does. So up here we get 149, and then we get minus 12. All right, so it's 2 times 149 is 298, so it's minus 12 plus 12, so I'm getting 310 here, minus 310. So the last check is 149. I'm putting them in the right order here. So that's S times A is 439 plus T is minus 310 times B, which is 211. So that's equal to 149 times 439 is 65411, 65411 plus, or it's negative actually, 310 times 211 is minus 65410, which is 1. Yay! Okay, so this makes a much better. As it turns out, this will be D, and this will be unimportant. So having a negative D would confuse the little proofs we're going to do later. So that concludes this very long section video on the extended GCD algorithm. Thanks.